Pre-Calculus Chapter 4, Lesson 6, and while this lesson covers a number of topics about periods, periodic functions, and what happens when you combine trigonometric functions, we're only going to look at 3 of the topics covered. We're going to look at what happens when you add a linear function to a sinusoid. How does that affect the sinusoid? Can we add 2 sinusoids together and get another sinusoid? And thirdly, we'll look at dampening a trigonometric function. So let's look at the linear, or what happens when we add a linear equation to a sinusoid first. Now, when you add a sinusoid, or when a sinusoid is added to a non-constant linear function, okay, we're not talking about a constant value, we're talking about a linear equation, the result is that the sinusoid is no longer periodic. The graph repeats its shape at regular intervals. In other words, it has the same shape to it. However, the y values are different on those intervals, or as it passes through these different intervals, the y values are not exactly the same. So while it looks like the same shape, it's not periodic, because a function is only periodic if in a certain interval the y values then repeat. So you put in more x values and you get the exact same y values out. And the adding of the linear function to the sinusoid affects the sinusoid in such a way that that does not happen. What does happen is the graph will show a curve that oscillates between 2 parallel lines. Whoop, got a lot going on here. I don't want that going on really. So you'll have this sinusoid looking graph oscillating in between 2 parallel lines. Now the question would be then, where do the parallel lines come from? I think maybe an example would be the best way to do to show you that. So in our example here we have 0.5x, which is a linear equation. That's another way to write it would be 1/2 x. So that's a line that goes through the origin and has a slope of 1/2. Okay, so that's a linear function, and it's being added to this sinusoid. Now, before we take a look at the graph, notice what's going to happen. If we think about what happens to the sine wave, it oscillates between a maximum of 1 and a minimum of -1. So we're going to have 0.5x, and we're going to be adding these different values up to a maximum of 1 and a minimum of -1. So if we think about the maximum value that we're going to add to this 0.5x, it's going to be 1, because that's as big as the sine wave is going to get. So there's one linear equation. And the sine wave also goes to a minimum of -1. So we're going to be adding a -1 to this. So now I have 2 linear equations. I have one line that has a y-intercept of 1 with a slope of 1/2, and a second line that has a slope of, a y-intercept of -1 and also a slope of 1/2. So the slopes are the same. The y-intercepts are different, so these are parallel lines. And so you're going to have these parallel lines, and then what's going to happen is this sine wave is going to be oscillating in between these 2 parallel lines as it goes up and down this way. Okay, so I have a graph of that. Let's take a look at that. So here you see I have the graph of 0.5x plus 1. It has a y-intercept of 1 and a slope of 1/2, and then the line 0.5x minus 1, and you'll notice that this sine wave, notice that it does oscillate in between these 2 parallel lines. Now notice that it does start at 0. Remember, the sine wave goes from 0, max, 0, min, zec, 0, max, 0, min, 0, and so the sine portion of this graph that has this linear equation added to it still starts at 0, and then you see it kind of oscillates in between these 2 parallel lines. So when we add a linear equation to a sinusoid, we're going to get this shape of the sinusoid oscillating between the 2 parallel lines. The parallel lines are determined by taking the linear equation that's being added to it, considering the max and min values of this sine function, and that creates the 2 linear equations. So if I had a 2 sine x, well, this 2 now means that the sine wave is going to reach a max of 2, so I'd be adding 2 to this linear equation and subtracting negative 2 from this linear equation, so that would move the lines further apart, but you still would then have that sinusoid oscillating in between those two parallel lines. Okay, so that's what happens when we add a non-constant linear function to the sinusoid. It no longer is periodic. It oscillates between two parallel lines. The next thing we want to look at is what happens when we add two sinusoids together or subtract two sinusoids. What relationship between the sine and the cosine will ensure that their sum or difference will again be a sinusoid. And what we're saying here is, if you read the discussion in your book, that if we add sinusoids with the same period together, then the resulting function will also be a sinusoid. If, however, I'm adding sinusoids together that do not have the same period, the resulting function is not necessarily a sinusoid. So only the fact that if we add two sinusoids together with the same period will that guarantee that we have a sinusoid as a result. So all we want to learn here or take note of here is that if we add or subtract sinusoids with the exact same period, the result will also be a sinusoid. So when we're looking at two equations, then all we need to determine is, will the periods or are the periods the same? And the only thing that's going to affect the period, you remember, is that B value, that horizontal stretch or shrink. So if the horizontal stretch or shrink value of each of the sinusoids being added together are the same, then the resulting function will be a sinusoid. If any of those horizontal stretches or shrinks are different, then the result will not necessarily be a sinusoid. So for a few examples here, if we take a look at 5 cosine x and 3 sine of x, we notice that the b value here is 1 and the b value here is 1. So the period of both of these sinusoids is going to be the same. Therefore, this resulting function is a sinusoid. In this example, we have a horizontal shrink of 1/5, and here we have a horizontal shrink of 1/3. So that means the periods are going to be different. So the result of this addition of sinusoids will not be a sinusoid. If we look at this example, again, we look at the horizontal shrink of 1/3. Here we have a horizontal shrink of 1/2. The periods then will be different. Therefore, the resulting difference of these two sinusoids will not be a sinusoid. And then finally here we have a 3/7 horizontal. Actually, this is a stretch of 7/3. This is a stretch of 7/3. And this is a stretch of 7/3. Because all of these horizontal stretches are the same, the periods of each of these sinusoids is going to be the same. Therefore, the resulting sum and difference of these sinusoids will also be a sinusoid. And the last thing we want to look at is what we call damping. And you'll notice from these examples that we have on the screen that here you have a sinusoid, and on this one you'll notice that it's being squeezed on the right side here. The oscillation is getting smaller and smaller. So what is causing this sinusoid to be squeezed as it moves towards infinity out here? And this one here is being squeezed, and then you'll notice this one here is being squeezed as well. This one goes through a squeezing and then rises back up, and it looks like maybe more squeezing going on out here. This property of squeezing something down is called damping, and it's called a dampening of the sine wave. Now, what causes that? And what causes that is when we multiply a sinusoid by an algebraic function. So if we multiply it by a linear function, or if we multiply it by a quadratic function or a cubic function, if we multiply a sinusoid by another algebraic function, that algebraic function is going to have the effect of damping or squeezing the sinusoid. Now, that function itself is called the damping factor. So anytime we see an algebraic function being multiplied by a sinusoid, we're going to have a damping effect, and that algebraic function is called the damping factor. Now, how does that work? Well, basically what we do is we take the damping factor function and we take its reflection over the x-axis, and between those two then the sinusoid is squeezed by those two functions. So we take the function that's being multiplied by the sinusoid, we take the reflection of that function over the x-axis, and together they cause a dampening or a squeezing of the sinusoid function. And what we're interested in is the damping factor, but we also want to notice of the limit or the direction in which the dampening is taking place. In other words, if I look at this function here, this function is getting squeezed as the x values go out towards infinity. So the dampening occurs as x goes towards infinity. Now you can have other functions where it's squeezed, let's take a look at this, may be squeezed like this. So the squeezing occurs as we go towards 0. So our dampening effects are either going to be as x approaches infinity or as x approaches 0. So let's take a look at a few examples. If we look at this first example, this 2 to the negative x is an algebraic function. It's an exponential decay. The function is decreasing. So we're multiplying this function by the sine of 4x. So this is being dampened. The dampening factor is 2 to the negative x. That's the dampening factor. Okay? The dampening factor is this function. Now, if we graph this function along with the opposite of this function, or its reflection over the x-axis, that will show us the dampening effect. So this is a decay that will go like this. Its reflection would go like this. So this sinusoid then is going to be getting smaller and smaller as it goes this way. So the dampening occurs as the x values go towards infinity. Okay, so dampening factor and the direction in which the dampening takes place. So here we have 2 to the negative x, so you can see, whoops, so you can see if we graph the function that goes down like this, and then this one goes up here, you can see that this sine function is getting closer, is getting squeezed as the x values go towards infinity. Alright. Let's take a look at negative 2x cosine 2x. The negative 2x is an algebraic function. It's a line. So there is a dampening occurring, and the dampening factor is that function. So the dampening factor is negative 2x. Now, if I graph negative 2x, that's a line with a slope of 2 that goes like this. The opposite of that, or its reflection over the x-axis, would look like this. So this sinusoid is going to be squeezed like this. So here the squeezing occurs as the x values go towards 0. As we come this way is when this squeezing actually occurs. Alright? Okay, and so here we have a graph of that. So you can see if I have, well, that's the reflection. Here's the line 2x, negative 2x, and here's the opposite of negative 2x. You can see that it gets squeezed as it goes towards 0 moving forward. So let me see if I can, you can pull this out a little bit further so you can kind of imagine, you can see as we get closer, you can see this line that would come down here as negative 2x, and here's a line of 2x. You can see how it gets squeezed as it goes towards 0. So as the values go towards 0 is when that dampening takes place. Okay, so the three concepts then that we want to learn in this lesson is when we add a linear function to a sinusoid, we're going to get a function that's no longer periodic, but we will have a sinusoid looking shape oscillating between two parallel lines. If we add two sinusoids together with the same period, the resulting sinusoid will also be periodic and will be a sinusoid. And then if we multiply an algebraic function by a sinusoid, we're going to get a dampening effect of the sinusoid. The algebraic function is the dampening factor, and then if we graph the algebraic function and its reflection over the x-axis, we can see at which direction the dampening is taking place, whether it's taking place as you're moving out towards an infinity one way or the other, or whether it's dampening or squeezing it as the x values approach 0.